Hi, everybody. My name is Rina. I'll just have to add that as a early career academic who's struggling with imposter syndrome, it gives me great nervousness to follow such incredible scholars and speakers. But I'll do my best to represent the work of myself and my colleagues of my lab. So the work I'll present is in. Uh, sorry, I cannot go to the next slide. Oh, got it. It's work that is being done in conjunction with my PI at Queen's University, along with two other institutions in the US, which are Memorial Sloan Kettering Cancer Center and MD Anderson Cancer Center. It was really interesting to me that Dr. Montgomery earlier also spoke about colorectal cancer because that is also what our lab is working on. Again, like not to go into too much of the details, but these are just some statistics. So colorectal cancer is the second deadliest cancer in the United States right now. And in terms of racial disparities, Black patients are recorded to be 20% more likely to get colorectal cancer than other groups, and Black patients that get colorectal cancer are 40% more likely to die as a result. So, um, in general, like about 1 in 25 people contract colorectal cancer, so it's a lot more common. But uh, if you include the earlier stage like that is indicative of it, then this number comes up to like 1 in 4, which is very high. And and this can be in multiple stages, which require multiple different forms of treatment. But of course, the one I'll be focusing on is the final stage, which is colorectal liver metastases. Usually, people that reach this stage have a very low chance of survival, and there right now a gap in methodology is sort of an automated way to predict the response at this stage, which would allow the patients to get personalized care. So to bridge this gap, our parent grant, which is also an NIH R01 grant awarded in 2009, is looking at a way to make accurate and robust imaging biomarkers for personalized treatment of colorectal liver metastases. And this is between the PIs, Dr. Simpson at Queen's University, who is my supervisor, Dr. Chan at MD Anderson, and Dr. Doe at Memorial Sloan Kettering Center. So this eventually led to a supplementary grant under ODSS, which looks into the ethical development of these imaging biomarkers. And as some of the speakers have already spoken about, AI models can learn bias through direct and indirect ways. And so that's sort of like the focus of this particular grant. So as Dr. Jeremiah has already mentioned, so we normally think of bias as uh, like a model's response to a sensitive variable, which could be gender, race, etc. But in reality, bias is actually more complicated. And I really like this iceberg metaphor for explaining it. So we can think of like the top of the iceberg is the statistical aspect of the bias. But oftentimes, if you just dig deeper, bias often hides more historical, systematic factors that affects marginalized groups. And the impact of bias of a model can be disproportional based on those groups. And we don't often know what the source and impact are because they're not clear or visible. So in terms of colorectal cancer, this is a survey paper that members of our lab worked on, and it's currently in revisions with BMC Cancer. But just to give you a sneak preview, some of the findings include that current studies, we need better features in relation to race and cancer incidence. So, for example, colorectal cancer incidence and race itself have a low correlation. However, mortality rate is, sorry, I wrote lower, it should be higher, is much higher for Black patients. So this is indicative that um, when we sort of like just have demographic information of race as a biological factor, we are missing out on a lot of information. Sometimes it's the socioeconomic aspects related to race that may be more relevant to the phenomenon we are observing here. In addition, we commonly see this phenomenon that is underrepresentation of Black patients in data sets. Currently, the problem that we are facing is that oftentimes the institutions we partner with are private institutions. And then if you ask a question of who has access to private institutions, then that can reveal like further like societal biases that are implanted into our data sets. And then we have the issue of self-fulfilling prophecies, that our models are very good at replicating historical patterns, but not very good at explaining why those patterns came to be. And therefore, like, if you account in automation bias, where like somebody could take a model's response as a matter of fact, we often see that we tend to trust models without really understanding why. So I just want to like touch on this other paper that formed a chief inspiration to the methodology that we wanted to take. And interestingly, Dr. Jeremiah has also mentioned this concept to some extent, which is that if we if a model is biased on a sensitive variable, we can train it on to predict that sensitive variable. So this was a paper in 2017, which also sort of like used this concept, but with specific data sets of X-rays, radiographs, mammographs, and CT scans. And these are all like publicly available data sets. No, actually, no, some of them are privately available, but some of them are publicly available. And they trained like 9 models to predict race in each cases. Usually the only racial variables they had access to were Black, white, and Asian. In some cases, they didn't have enough numbers of Asian in representation, so they only rated Black or white. And I don't want to sound like a clickbait article, but the results may surprise you. So the results were that like there was about the AOC ROC was about 0.98 to 0.96 for all these racial categories. So it's almost like perfectly predicting race in each cases. And if you look at the saliency maps that developed, like these figures where the model is focusing on made no sense to like experts. And their conclusion was that there is no biological basis for this prediction. So how are models so good at understanding like what is race from an X-ray? And based on this, like their further conclusion was that a model could be biased on race in such a way that an expert might not even realize it, and might not even realize this model is biased when it's in practice. And again, when we don't have the demographic data in front of our hands, as Dr. Jeremiah mentioned, that we might not even know this model is biased. So now, given that we're a bit of a lab of skeptics, and we kind of like initially saw this and were like, wait, this can't be true. And so my supervisor said that, hey, what if there's overfitting? Like the authors didn't test for overfitting. So we kind of like went, this is a paper my supervisor worked on where we use a method known as response permutation in comparison to AUC. The idea is if you have a signal predicting a response, if you scramble up randomly the input responses in relation to the images, you can essentially you're supposed to get like a random data set. And if you tried predicting the same variable, you should be getting like an AUC of 0.5 ideally, right? Because you are predicting on a completely random scrambled data. And if you repeat that process several times, you can sort of like check like, was there anything in the data that could potentially lead to overfitting, that could lead to the response we're getting? So we tried this on some of the data sets in the previous paper we showed. So we recreated the model. Obviously, we used a lot less computational resources than they did, but we did get like some pretty good results, even with the resources we had. And we tried our permutation technique. So we did like 10 permutations, and our results were that the AUC on the permuted data sets were very close to 0.5, so which indicates that there is low evidence of overfitting. Now, there could obviously be other factors that we haven't looked into, but we also like this made us like kind of like take the author's interpretations a little bit more seriously. So what is like if the models are seeing something, what is it that they're seeing? Are they seeing sort of like societal factors that are in relation to our bodies? So like poverty, access to healthcare, insurance, food security. How do these impact our bodies, and how do these reveal themselves in sort of our biomarkers? And like without accurate information, we can't really represent them in our data. And then also a question of how does AI bodies view other marginalized groups? for example, as a trans person myself, like the question that always I wanted to ask is, how does AI see transgender bodies? Might be out of scope of this project, but again, like it's a burning question in my head. So, what our next steps of our research right now is that we have this incredible amount of data that's really high quality from these institutions, which include like CT scans of livers for people with stage 4 colorectal liver metastases. We want to replicate this process of trying to predict the sensitive variables from this data and observing if there is ability for it to recognize race or if there's a bias that is detectable. And we want to understand those findings from a social and ethical perspective. I think I'm running out of time, so I'm going to wrap it up here. I do want to very quickly mention, though, part of our goals of the grant was to make AI discussions of AI bias more accessible, and one of the results is this podcast. It's an incredible podcast. I really hope some of you get a chance to listen to it. And there's also this other podcast, Responsible Use of AI. Again, both are excellent, excellent hosts. I really, really recommend it. Thank you so much, everybody. I'm taking one at the back first. Don't go anywhere. Um, I think the idea is like the image, so the image that we're using that's related to the data, there should be a correlation. So if you scramble up the labels, then the correlation should be broken, and you're supposed to be getting at least, even if it's not exactly zero point 0.5, at least something like that's close to zero point 0.5. I think the idea there is that if you have an imperfect model, then that means that initially the model is not really learning those correlations. It's just learning something else in the image. And even if you scramble it up, it could still be learning that something else that we're not aware of. And therefore, we expect to see an ROC that is not exactly zero point 0.5, might be zero point 0.6 or something, but that would be more of an evidence of overfitting from my understanding at least. That's